All right, let's start with a nightmare scenario.
Yeah.
You're running a major tech platform, things are going great, you've got steady organic growth, and then between January 2023 and February 2025, your server traffic doesn't just double, it doesn't triple, it spikes by 50 times.
50. 50. That's a terrifying number. Most systems start to creak when they grow by 50%. 50 times is basically an architectural extinction event.
Exactly. We are talking about Agoda, the massive digital travel platform. And this isn't just about handling volume, it is about handling it fast. In the travel game, if I search for a hotel in Tokyo and that page hangs for 3 seconds, I'm gone. I'm already booking somewhere else.
Oh, for sure. And Agoda's target for this is a P99 latency of 10 milliseconds.
Which is just,
Yeah.
it's faster than the blink of an eye. Literally.
Yeah, a blink is about 100 milliseconds, so they need to be 10 times faster than that, no matter how much traffic is hitting them.
So, today's deep dive is based on a really fascinating case study. It was presented by Warwick Isaratham at the Monster Scale Summit 2025 and also detailed in the news stack. It's a detective story.
It really is.
It involves a bursty crisis, a hardware bottleneck that physics just wouldn't let them ignore, and a team of engineers basically MacGyvering a database to keep the business alive for months, all while waiting for parts to arrive.
It is a classic engineering thriller, and honestly, it challenges a lot of the modern cloud mindset. We tend to think, the code solves everything. If it's slow, optimize the algorithm. If it breaks, patch the software.
Right.
Agoda's journey proves that sometimes you just can't code your way out of a physics problem. Sometimes the hardware, the actual metal wins.
Okay, so let's unpack this. To understand why this crisis was so severe, we have to look at the specific system that was under fire. It's called Agoda's Feature Store.
Yeah, we should probably clarify what that is.
Please do, because Feature Store sounds like a place I'd go to buy a plugin or maybe an upgrade.
Oh.
Laughs. No, nothing's for sale there. In the world of machine learning, a feature is a piece of data that helps a model make a prediction.
Okay.
So things like, is the user on a mobile phone? What's their average spending history? Is this IP address associated with bots? All these little data points.
So it's the context, the clues the AI needs to do its job.
Precisely. And every time you load a page, Agoda's models need to grab these features instantly to decide what to show you. They are serving about 3.5 million of these entities every single second. It is a massive high-velocity repository.
And the architecture to support that is pretty sophisticated. The source material outlines this tiered approach. They have client-side caching, then something called DragonflyDB as a high-speed temporary cache.
And finally, ScyllaDB as the persistent source of truth, the actual database where all the data lives.
And that hierarchy is key,
No,
right?
absolutely. In a perfect world, you want everything served from the cache. DragonflyDB is in memory. It's lightning fast. You only want to hit ScyllaDB, the disk-based database, when you absolutely have to. Which brings us to the inciting incident. Mid-2023, everything is humming along. And then a new internal user onboards to the feature store. This wasn't a slow rollout. It was a new application that had a very specific and very dangerous traffic pattern.
They called it super bursty.
Which sounds kind of cute, but I'm guessing it wasn't.
Not even a little bit. Bursty in this context meant the traffic was dead silent for long periods, and then boom, triggered by some external signal, it would just flood the system with requests.
And the volume wasn't the only problem?
No. The problem was that these were cold cache scenarios.
Right, because the traffic was so sporadic, the data wasn't sitting in the cache waiting to be read.
Exactly. The cache was empty. So when that burst hit, and we're talking 120,000 requests per second, every single one of those requests found an empty cache and just punched straight through to the database layer.
And to make matters worse, they ran into something called the cache stampede. I love that term, by the way. It paints such a vivid picture.
It is exactly what it sounds like. Imagine 10,000 people all asking for the same piece of information at the exact same millisecond. The first person asks, the system sees it's not in the cache, and it goes to the database to fetch it.
Okay.
But before that first request comes back, the other 9,999 people also see an empty cache, and they also run to the database.
So instead of one database query to populate the cache for everyone, you get 10,000 identical queries just hammering the disk all at once.
And ScyllaDB, as robust as it is, just couldn't swallow that spike. Agoda had 2 data centers handling this load. One of them slowed to a crawl, the other one completely collapsed.
Wow.
The source says it fast failed, which is a very polite way of saying it just fell over. Retries piled up so fast that even after the traffic stopped, it took 40 minutes just to clear the backlog.
40 minutes. In the travel industry, that might as well be a year. If I can't book a room for 40 minutes, I'm on a competitor's site in 40 seconds.
Exactly. It was a critical incident.
So this is where the detective work really begins. They have 2 data centers. Presumably, they're mirrors of each other. Same code, same configuration, same traffic. One barely survives, the other one dies. Why?
That is the million-dollar question the team asked. They audited everything. They checked the software versions, the network topology, the code. Everything was identical.
So they had to go deeper.
Yep. They looked at the hardware, specifically the storage disks.
And what did they find?
The data center that survived was running on NVMe SSDs. The one that failed, the one that caused the crisis, was running on older SATA SSDs.
You know, I feel like we see these acronyms when we buy laptops, but we don't think about them much. SSD is SSD, right? It's all flash memory. Why did the interface SATA versus NVMe make the difference between life and death for their database?
Well, it really comes down to how they handle traffic. SATA is older technology, designed back when we used spinning hard drives. It's a serial protocol. So think of it like a single-lane road. It doesn't matter how fast the cars are. If you have 10,000 cars, they have to queue up one by one.
And
NVMe Non-Volatile Memory Express was built from the ground up for flash storage. It's essentially a 64,000-lane superhighway. It supports massive parallelism.
So what was the difference in performance?
When Agoda ran the benchmarks, the NVMe drives offered 10 times the read performance of the SATA drives. 10 times.
So it wasn't a code bug at all. It was a physics problem. The SATA drives physically could not clear that queue fast enough.
Correct. The queue depth just exploded, latency went through the roof, and the system timed out.
So the solution seems pretty obvious here. Just buy more NVMe drives, upgrade the bad data center, problem solved.
In a perfect world, yes. But supply chains are messy. They placed the order for the new disks immediately, but the vendor came back and said, great, we can get those to you in 3 months.
Ouch. So you're sitting on a burning platform, you know exactly what the fire extinguisher looks like, but it's on a boat somewhere for the next 90 days.
And the fire's getting bigger. Remember, Agoda's organic traffic is growing anyway. They calculated that even without the bursty user, they'd hit the physical limit of those SATA drives in about 8 months. With the bursts, they were already past the breaking point.
This is the part of the story I love. This is the real MacGyver moment. They couldn't change the hardware. They had to figure out how to tune the software to make those clunky old SATA drives perform like race cars.
It is engineering survival mode. Step 1 was just stopping the bleeding. They worked with the internal users to implement aggressive client-side caching.
Okay.
Essentially, they put a bouncer at the door to smooth out the bursts. That dropped the load from 120,000 requests per second down to about 7,000.
That is a massive reduction.
It saved the patient, yes. But 7,000 requests per second was still dangerously close to the SATA limit. They had zero headroom. If traffic grew even a little bit, they'd crash all over again.
So they needed to get that headroom by tuning the database itself.
And to tune it, first they had to break it.
Right. You can't optimize what you can't measure.
Exactly. They set up a test environment and replicated the failure, sending traffic directly to the database to bypass the cache. And they found that the baseline capacity of those SATA drives was a measly 5,000 entities per second.
Okay, so that's their starting point. Their first attempt was something called data modeling. Walk us through that.
The theory was pretty logical. They thought, maybe our data's too scattered. If we split the tables by feature set, organize the data into smaller specific buckets, maybe the database can find what it needs faster, like organizing a messy drawer into neat little dividers.
And then did it work?
Absolute failure. Zero performance gain.
Why? That seems so intuitive.
It is intuitive for us humans.
Yeah.
But for the disk, it didn't matter. Logically, partitioning the tables didn't change where the bytes physically lived on the disk.
Yeah.
The controller still had to do the exact same amount of work. It was a software abstraction that didn't solve the hardware reality.
Okay, so strike one. Next up, they looked at the compaction strategy. Now, this gets a little technical, but it seems like this was the real turning point. What exactly is compaction in a database like ScyllaDB?
So ScyllaDB uses a structure called an LSM tree. When you write data, it doesn't overwrite the old entry. It just writes a new file called an SS stable with the new info. Over time, you end up with hundreds of these files stacked on top of each other.
Like a stack of memos on a desk.
That's a great way to put it. And if you want to find the latest memo about user X, you might have to look through 10 or 20 different piles to find it. Compaction is the background process that merges those piles into one clean master file so you don't have to hunt around.
And Agoda was using the default strategy, which was size-tiered compaction.
Right, which is the industry standard for a reason. It's great for writing data quickly. It's lazy in a good way. But Agoda didn't have a write problem. They had a read problem.
Because with size-tiered, the data isn't perfectly sorted.
Not at all. To find that one specific user feature, the database might have to check 8 or 10 different SS tables on the disk. And remember, on a SATA drive, every single check is expensive. They discovered they had massive read amplification. To read just 1 kilobyte of actual data, the system was reading 70 kilobytes from the disk.
A 70-to-1 inefficiency ratio. That is staggering. It's like buying a pack of gum and having to carry the entire vending machine out of the store.
It's a perfect analogy. So they switched to leveled compaction. This strategy is much stricter. It spends more CPU cycles to keep the data perfectly sorted and separated. The guarantee is that a specific piece of data will likely only exist in one file at a specific level.
So instead of checking 10 files, the disk only has to check 1.
Exactly. They traded CPU power, which they had plenty of, to save disk I/O, which they were starving for.
And the result?
Throughput jumped by 50%. They went from a baseline of 5,000 to about 7,500 operations per second.
Better. But still not quite enough to sleep soundly at night.
No, not yet. So they had to turn one more knob, S-stable summaries.
Okay, summaries. This sounds like some kind of index.
It is exactly that. ScyllaDB keeps a summary of the data files in RAM, so it knows where to look on the hard drive. But by default, to save memory, that summary is a bit vague. It points you to the general neighborhood of the data, but not the specific house.
So the disk still has to do some scanning in that neighborhood to find the right address.
Right, and scanning takes time. So the Agoda team decided to make that index much, much more granular. They increased a setting called stable summary ratio by 20 times.
So instead of pointing to the neighborhood, it's now pointing to the exact house number.
Precisely. This meant the summary file grew massive. It ate up gigabytes of RAM. But again, look at their resources. They were poor in disk speed, but rich in RAM. They spent their memory budget to buy disk precision.
And that was the real breakthrough.
It was. Combined with the compaction change, their capacity on those old SATA drives jumped to 20,000 entities per second.
Wow.
That's a 4x improvement over their baseline.
They quadrupled the performance of 5-year-old hardware just by twisting a couple of software configuration knobs.
They gave them exactly what they needed. Breathing room. They weren't crashing. They could handle the organic traffic and the smoothed out bursts. They survived the 3-month wait.
And then the truck finally backed up to the loading dock.
The NVMe drives arrived.
So we saw that jump from 5,000 to 20,000 with just the software tuning. What happened when they finally plugged in the new hardware?
The capacity skyrocketed to 300,000 entities per second.
Wow. Okay, let's just sit with that for a second. 20,000 with the best engineering tuning they could possibly do, and then 300,000 just by changing the disk.
It's humbling, isn't it? The software tuning was brilliant. It absolutely kept the business alive. But the hardware upgrade was a sledgehammer. It offered a 50x to 60x improvement over the original baseline.
It really validates that idea that physics wins. You can be the smartest coder in the room, but if your electrons are stuck in a single-lane queue, you are going to lose to the person with the superhighway.
Absolutely. The software tuning removed logical inefficiencies, but the NVMe drives removed the physical constraint. And, Agoda didn't stop there. The source mentions that once the fire was out, they continued to optimize.
Yeah, they mentioned a rewrite in Rust.
Right, they're moving the application layer to Rust to get better memory safety and raw speed. And they implemented permanent cache stampede prevention.
Which is basically logic that says, hey, if someone is already fetching this data, everyone else just wait a millisecond, don't send a duplicate request.
Exactly. It solves that crowd at the door problem logically. And they also mentioned a future experiment called data remodeling.
This was interesting because it kind of circled back to their first failed attempt.
It did. Remember how splitting the tables failed? Well, they realized that since they almost always need all the features for a user at once to make a prediction, why store them as separate rows?
Right.
They're testing storing all features in one giant fat row.
Just grab the whole blob in one go.
Yep. It reduces the number of lookups to 1. Preliminary tests are showing another 35% performance boost.
Yeah.
But it requires migrating terabytes of existing data into a new format, so that's a massive project for another day.
There's always a backlog, isn't there?
Always.
So stepping back from the weeds of compaction strategies and summary ratios, what is the so what here? Because most of us aren't running systems at Agoda's scale.
I think the lesson is about full stack awareness. And I don't just mean knowing JavaScript and Python. I mean understanding the connection between your code and the metal it actually runs on.
Hmm.
Wurakar and Azertham admitted that Agoda had been using ScyllaDB for years without tuning these settings because they never had to.
They were driving a Ferrari in first gear.
Exactly. They just assumed the database and the cloud infrastructure would handle it. We all do this. We spin up instances on AWS or Google Cloud, we pick a medium size, and we assume it's infinite. We rarely ask, what is the queue depth of the attached storage volume?
Until traffic spikes 50x and it forces you to ask.
Right. When you hit real scale, those little implementation details become major architectural constraints. And I think there's also a huge lesson here about matching your configuration to your specific workload.
The read versus write thing.
Yes. There is no best database setting.
Yeah.
Leveled compaction saved Agoda because they were read-heavy. If they had been a write-heavy logging system, leveled compaction might have killed their performance. You have to know your traffic pattern.
It puts a lot of responsibility back on the engineer. You can't just trust the defaults.
Defaults are made for the average user. If you want high performance, you have to deviate from the average.
So here's a provocative thought to leave our listeners with. We live in this era of abstraction. We have serverless, we have Kubernetes, we have AI writing our code. But looking at this story, how many performance issues are we trying to solve with complex code, caching layers, retries, complicated logic that could actually be solved just by checking what kind of disk we are running on?
I would bet money that half the engineers listening right now have a retry loop in their code that only exists because their database disk is too slow. Or they're building a Redis cache they don't actually need because they haven't tuned their compaction strategy.
We're over-engineering software to fix under-provisioned hardware.
It is the trap of modern development.
Yeah.
Sometimes you don't need a new algorithm. You just need to read the manual, tune the config, or what how it meant. Just buy the faster drive.
And hope the truck doesn't get stuck in traffic.
Exactly.
Well, a huge thank you to Wurakar Azertham and the team at Agoda for sharing this story. It takes guts to stand up at a conference and explain how your data center fell over.
It really does. Transparency like that is how the whole industry learns and gets better.
And thank you to the Newstack for the detailed reporting. If you want to dive deeper into the specific config settings, we'll have the link in the show notes.
Definitely worth a read.
That's it for this deep dive. Go check your stable summary ratio, everyone. We'll see you next time.
Happy scaling.